Let us start lecture 5, and the course is phase diagrams in single component and binary systems. And today we will take the topic concept of equilibrium. We have already started discussing about concept of equilibrium. In fact, we started with macro state, and we really understood that macro state is also nothing but a state of equilibrium. And we could understand that in order to define a system existence, we make use of system variables, and there we saw that if a single component system, we need only two independent variables, pressure, temperature. Let us say if we take independent variables, then the last one, which is the dependent variable V, can be found out from equation of state. Let us say if it is fixed composition and also multi-phase, multi-component system, then also we can actually we have to specify two independent variables, because we are fixing composition. Okay. And since we are fixing compositions, so we would have considered, we would have four variables like pressure, temperature, volume and composition. Since we are considering fixed composition, then if we fix two variables, the last one, which is the remaining one, can be found out through the equation of state. Okay. Now, we have also discussed about the equilibrium concept little bit, like let us say a system is left to itself, and when the defining variables are also unchanged, the system would also remain unchanged. That means, we actually take a consideration of state of rest. Okay. So, system is unchanged means the system is maintain its position, its condition under the unchanged variable condition to be same. Okay. Now, we have also talked about three types of equilibrium. One is thermal, another one is mechanical. Thermal means the temperature of the system is equal to temperature of the surrounding. Mechanical is when the pressure of system is equal to pressure of surrounding. So, there is no unbalanced force, and we have talked about compositional equilibrium. So, now when we talk about compositional equilibrium, last class we have not talked about, we did talk about that if a single component, definitely composition would remain same, but if it is multi-component and there could be possibility of multi-phase situations, that time the equilibrium will not be decided by the same composition. Rather, we have to bring in one more term, which is called chemical potential. And when we talk about chemical potential, we have to talk about chemical potential of a component in a phase, if that is equal to the chemical potential of the same component in other phase, if these two things are equal under the fixed other variables. Okay. For example, if we consider pressure, temperature and composition to be the independent variables, and then you have volume, that becomes dependent variable, and if we take pressure, temperature to be constant, then only one situation that is left out, which is composition. But in case of multi-component system, we have to bring in chemical potential. We will do that later. Since compositional equilibrium does not mean similar composition, rather it is the same chemical potential of a component in different phase, that should be equal. So, that is what the composition equilibrium can be termed as a chemical equilibrium. So, we have three types of equilibrium. One is thermal, then mechanical, and then compositional term we will not use, because in case of multi-component system, the similar composition does not mean equilibrium. So, we will see that later. Okay. Compositional equilibrium will change this term to chemical equilibrium. Chemical equilibrium. Okay. So, these are two other equilibrium. So, this is nothing but T system equal to T surrounding, P system equal to P surrounding, and here since we are considering chemical potential, chemical equilibrium, we bring in chemical potential which is termed as mu. Mu I, let us say I is one of the components in that multi-component system. Let us say phase 1, there are two phases, phase 1 should be equal to chemical potential of I in phase 2. So, that means the system is in chemical equilibrium with respect to component I in both the phases. So, that way we narrate our equilibrium. But this chemical equilibrium will be talked more when we bring in binary phase diagram conditions. But otherwise in case of single component, since the composition is same everywhere, so we do not bother about it because it is a single component. So, that time equilibrium will be decided by the variables like pressure, temperature or temperature volume or pressure volume, because the third one will be decided on the basis of equation of state. Now, these equilibrium conceptually can be termed as stable, metastable and unstable. So, this equilibrium can have these three modes. So, if we want to understand stable, metastable and unstable, we can take consideration of energy as a function of let us say distance. Okay. So, now and this one we would understand better when we talk about different the second law of thermodynamics. We will touch upon that, and there you would understand why energy needs to be brought in order to understand equilibrium. Okay. So, now there if we have a situation like this kind of situation, now which one has the lowest energy? The lowest energy is here, and another energy level is this, and this lowest energy there is a basically shallow region. Let us say I put a ball, and that ball if I do not leave this ball, let us say consider that ball is a system. So, if we leave that ball there, so that ball will stay there, it will, if we do not push it, it will stay there. Okay. And similarly, if I put a ball here just at the peak of that particular pattern, that ball if we do not touch it, do not make a kind of push something like that, it will never fall to either side. But there is a difference between these three situations, and every situations if you see, if we consider energy to be E, so I can see that dE, that slope of that particular position, so d distance, let us say this is d, let us say this is instead of d, I can put it as A. So, I can say dA should be 0, dE dA equal to 0, dE dA equal to 0. So, at every point if I take a slope, that slope becomes 0. Okay. Now, once I have that situation, let us understand the difference between those positions. Now, let us say if I put a little movement here, let me just disturb a delta disturbance, which is a very infinitesimal disturbance if I put there, then this ball will have a kind of vibration, but finally it will again fall back to this position, and it will stay there. Similar happens here, but here situation is different. Here what happens, if I do a little vibration, even it is a small vibration if we put, then this ball it will fall on the this side or this side, okay, and then there will be free fall because there is no resistance. And if I take this path to be no friction slope, then definitely the ball will fall to either side of that particular hump. So, then this particular region is called unstable rest. This is called unstable rest, and since we have considered this equilibrium to be a state of rest, okay, so this is also a state of rest. So, I can take it as an equilibrium, but here equilibrium is that rest is very unstable. So, I can put it as unstable equilibrium. Now, let us consider now these 2 points. Let us say I mark it as 1 and this is 2. If I try to understand 1 and 2, if I let us say put little bit of energy to this and I push it to this peak position, which is the unstable rest, and then I further push it, then what would happen? The ball will move to this place. And if you see within this particular plot, there is no other place where the ball can rest other than that particular place 2. Okay. So, and that place 2, if I see the energy axis, that has the lowest energy within this configuration. So, now whenever, now this is also rest, these 2 are 1 and 2, both are rest positions, this is also rest. So, that means that is equilibrium. But if I give little energy to this, from higher energy level rest to a lower energy level rest, it can go, and those 2 energy levels are seemingly stable. Okay. But since one has lower energy than the other, then the lower energy place should be considered as stable rest, and the other one which is also stable, but there is a possibility that if I give little energy, little push, so that it goes to the hump and then further push, it goes down to the lowest point in that configuration. So, both the rest can be termed as this one, which is the final rest positions, can be put it as stable, and this one can be put it as metastable, and we can call it metastable equilibrium. And this is stable equilibrium. Okay. So, now you understand that this within this configuration I can have these 2. Now, let us understand a practical situation. Let us consider that I have a roof and then there is a fencing, a thin fencing, and then there is a platform down there. Okay. So, now if I put a ball on top of roof, then that position becomes metastable equilibrium, metastable rest. And then if I put the ball and rest it somehow on top of that thin edge or the thin barrier top, then I can actually, if I do not give any disturbance to that ball, it stays there. So, that is also basically unstable rest. So, it becomes unstable equilibrium. And then if I consider the platform below there, or let us say the surface of the earth, that becomes actually a kind of stable rest. So, that becomes stable equilibrium. So, that is a kind of analogy we can have. Now, once we have these analogy, then let us understand more about this equilibrium. So, when we talk equilibrium, now we have to also see that for example, one state changes from one place to another place, just like we considered that pressure, volume, temperature map, and then we understood that volume is a state function. We drew some diagrams and we saw that volume becomes a function of pressure and temperature. Whether we take one path or different path, finally the change of volume does not depend on the path. So, that is what volume becomes state function. Similarly, pressure and temperature also basically state functions. That means it does not depend on path. And there are some variables, some parameters, some aspects of thermodynamics which are path dependent. We will see that heat and work that should be considered in order to understand equilibrium. So, there those change of heat or change of path can be path dependent. Okay. So, like that there are variables which are state dependent or state functions. So, which depends only on the final and initial state, and the path functions which are dependent on the path it takes. So, and the state functions, this is a fantastic concept, and you would see that depending on the state function we take reference values, okay, and then we do not bother about the absolute value of those state functions when we consider equilibrium absolute values, rather than we consider the difference in values in order to find equations for calculating equilibrium between two phases and thus calculating phase diagram. Fine. Now, when we talk about these systems, we have to consider one more situation. So, that is called internal energy. Now, we are gradually getting into energy. So, internal energy in thermodynamics is termed as U, okay. And then there will be another term which is basically work, and then another term which is basically Q. Q is work, W is work, Q is heat, fine, and internal energy. Now, there is a fantastic relation between these this particular three things, and what is internal energy we will see little later. At this moment, let us consider that the system possesses some energy which is internally stored. So, consider that. So, physical aspect of internal energy we will understand little later. Now, when we talk about energy, so we know that energy is conserved, fine. So, we say that energy cannot be destroyed or cannot be created, but there is one more concept: energy can exchange, energy can change from one form to another form. So, now energy can actually change to work also. For example, if I consider J to be Q to be W is basically the work, and let us say Q is the heat energy, and work is also a form of energy. So, there will be equivalence, there will be exchange. For example, work can transform to heat or heat can transform to work, but that change will have an equivalence. So, what is that equivalence? The equivalence is basically, it is a basically mechanical equivalence of heat. This is a famous Joule experiment, it proves that. Now, if I consider energy which is, let us say, W and Q, so both are energy. So, this is proportional, because we know that energy cannot be destroyed, it cannot be created, but there can be changeover from one form to another, but there will be an equivalence. So, these can be written as W equal to JQ, where, and the Q sometime it capital Q it is written, okay, and this W can also be capital W. We can exchange depending on our convenience. Now, here this J is basically mechanical equivalence of heat. Now, here J value is around 4.2 joule per calorie. Okay. So, now you see that if I have 1 calorie spent, then I would be doing 4.2 joule work. Okay. So, this is equivalence. Now, when I consider internal energy, work and Q, let us consider a closed system. Now, we see, let us consider a closed system. Simple system, let us say ideal gas, an ideal gas, a single component gas, and why we are taking it? To set up a relation between U, W and Q. Now, when we talk about ideal gas, now we have already talked little about that ideal gas is the one where molecules would have very little interaction. In fact, if you take a gas and let us say a few molecules of that gas, let us say the size is small. When we talk about size of a gas, we say that the number of molecules of that gas is very low. Okay. If I take 1 mole and if I want to, that becomes my size. So, now if I take 0.1 mole, so the number of molecules will reduce. Let us say I have taken a consideration that it is a closed system and I have taken 100 molecules of a gas. Now, once I take that, let us say I reduce the pressure. So, how can I reduce pressure? So, either I have to increase the volume. Let us say if I fix the temperature, if I have to reduce pressure. So, if I consider PV equal to RT, let us say for 1 mole of ideal gas. So, then R is an universal gas constant. So, P proportional to 1 by V if we fix the T, T is fixed. Okay. So, that time if pressure is reduced, then volume has to be large for a particular size of the gas. So, once volume becomes very large, then what happens? The distance between the atoms or in this case molecules would be so large that there will be hardly any chance for the molecules, 2 molecules to hit each other. Okay. So, that means interaction becomes minimal. Similarly, if I increase the temperature, let us say I fix the pressure. So, V proportional to temperature, pressure fixed, fine. So, that means if I increase the temperature, volume would also increase. Again the similar situation, the distance between the molecules would be so large, it will be very difficult to have interactions. So, when there is no interaction between the molecules, so we call it as an ideal gas. Now, that case, if I consider that, now let us say I take 2 systems, one is system A, another system is system B, and these are all a rest position and it is basically macro state. So, from one macro state A to another macro state B, it is moving, the ideal gas is moving its position from state 1 to state 2. Now, for that let us say I have some energy U A for the system and internal energy. Internal energy we have already talked that it is a system energy within. Okay. So, now if I send some heat, let us say Q amount of heat, then what is the total energy of the system? U A plus Q, this is my total energy of the system. Now, when because of this Q is absorbed by the system, okay, then the system energy goes up. Let us say because of that it does some work. So, and because of that work and because once you send Q, it starts changing its state. So, while changing that positional change state A to state B, it actually does some work. So, that work let us say W, and when it does work, so then the system, the state B would have internal energy U B. Okay. So, the total energy of the state B would be U B plus W, okay, because the amount of work is actually done by the expense of some energy of the system, and because of that internal energy also changes, fine. Now, here I have taken W, when W is done by the system I have taken it sign as positive. When Q is absorbed by the system it is taken as positive. So, the concept what we follow is Q is positive when heat is absorbed by system. Q becomes negative when heat is released by system. W is positive, work is done by the system, and W negative, work is done on the system. This sign convention will follow. So, now you see from one state A to one state another state B it reaches by absorbing heat and doing some work W. So, that means there is only the game of energy, and the total energy before and after the change should be same, because we know that energy cannot be created or destroyed. So, that means these two should have been equal. Once we have this equal situation, then I can write it as U. What is the final state? Final state is B. So, U B minus U A is basically the initial state. It becomes Q minus W. So, this is becoming del U equal to Q minus W. So, this is also a statement of first law of thermodynamics. Okay. So, from here we will try to understand isolated system. Okay. So, in the next class we will try to understand isolated system, and gradually we will get into some situations like different changes like adiabatic change, isothermal change, and then we will bring in one more concept called reversible change. And this reversibility is nothing but a kind of unchanged equilibrium when a system goes from a state to another state. This is a kind of hypothetical concept, but that concept guides us to lot of formulation for equilibrium consideration of different phases, and that would lead to phase diagram. So, let me stop here with this. So, we will continue our discussion on concept of equilibrium with the help of energy consideration. Thank you.